See, till now we have done some linear algebra, some complex numbers, and we have done some understanding of Lagrangian, and we have done some understanding of Hamiltonian. We also have had some understanding of, how do I say, of the introductory quantum, right? Some intro to QC. So this is what we have done till now. Everybody clear on this, right? So now what we will do for the next couple of classes, we will get into some quantum mechanics, okay? Which just means that we will get into quantum mechanics will be about 3 hours we will do. And then we will get into quantum computing again. So what does it mean? We go back to quantum computing. At this point, we will go back into coding with Qiskit and then algorithms, right? We'll actually get into details of the existing algorithms and hopefully try and build a couple on our own, however bad they may be. Maybe in here, one or two other times we may have to discuss classical computing also, because I don't know if everybody understands classical computing to that level either. Right? Is this clear?
Yes, sir.
Yeah. So today we will actually talk about a particular part of quantum. So yeah, so before we get there, what is quantum mechanics, right? Anybody has any idea? What is it? What is quantum mechanics actually? Okay. So see, here is one way to understand this, right? Now you have Newtonian mechanics. We talked about Lagrangian mechanics. We talked about Hamiltonian mechanics. Now we're talking about quantum mechanics. See, the way to understand this is quantum mechanics is a framework. It's a framework to understand how to describe the state of any system. Okay. So for example, in Newtonian, how did you describe the state of a system? Right? In Newtonian, it was forces. Right? In Newtonian mechanics, you used forces to describe the state of a system. So similarly, when you went Lagrangian, you took energy. When you kind of went to Hamiltonian, it was more of entropy based. Okay. And when you get into quantum mechanics, we will see this is basically the wave equation, right? The wave based, the wave particle duality, superposition. Okay. So it's a framework. Now, when I say mechanics, don't get confused that it's only for mechanics. The framework can be applied to anything. Newtonian mechanics applied to electricity gives you Maxwell's equations. So, that's a framework of trying to understand something by understanding the forces acting on it. If that is the underlying framework, then whatever you get is whatever you get, right? So mechanics just doesn't mean, because there is a terminology, right? A lot of people get confused. Then mechanics, oh, it's all about throwing a ball or moving a pendulum. No, mechanics is anything. Newtonian mechanics is anything where Newtonian framework is applied. Similarly, quantum mechanics is anything where quantum mechanics is applied as a framework. Okay, it can be to the theory of relativity, it can be to anything actually. To computing becomes quantum computing. Right? Is this sort of, there's no confusion here, right? So today the way we will do is I want to make it a little more interactive, because otherwise I think I'm just talking, I'm not sure if anybody is getting anything. So the whole point is this. Today we'll try and understand superposition. I think we talked about it a little bit. I think everybody nodded their head, but I was not very clear how much anybody understood. Okay. Now, let us take electrons, okay? Let's simply take electrons. because this is all about electrons. From now on, it's going to be either an electron or a photon that we're going to talk about, right? Let us say, see, I thought about this and then I thought maybe I'll simplify it initially so that people are clearer and then we'll get into details. So maybe think about there are two properties, right? Let us think electrons have two properties called color and hardness. Okay. Let's just think for now. They have two properties. The color can be either black or white. That's it. So nobody has seen an electron that is of any other color. People have only seen electrons which are either black electrons or white electrons. Similarly, people have seen electrons which are either hard or soft. You can see, right? These can be other things like position or momentum or whatever else that you want, like spin or any other observable. But right now, let's abstract that whole thing and first learn the concept, and then we'll get into what is those. Okay? And again, an electron can be either hard or soft. There's nothing like it's jelly-like. There is no such state. There are only two states, binary. Okay. And let us also now think. Now let's imagine you create some sort of an equipment to measure. Right. Let's say this is the black box to measure. You have an aperture for input, so you can send electrons through this, and you have two output apertures. Okay. Let's just say there's a color box. So let's say all black electrons come from here and all white electrons come from here. So how do you know whether something is black or white? By position. If something is in this aperture, you know that there is, you know it is white, and in this aperture, you know that it is black, right? Now, how do we build this? It's not important. For this stage, you can think there are some hyper intelligent monkeys sitting in there. You know, you don't care. You can actually say there is a monkey sitting in here that actually sorts electrons. Okay, it doesn't matter what we do because we can build the same thing using so many techniques. But for now, think of them as monkeys. But something is coming in black, white. Okay. Similarly for hardness, right? Yeah. You have something which is input. Let us just say soft and hard. Okay. Hard electrons come that side, soft electrons come this side. So you have built this equipment here. So up till this, very, very simple. Nothing great I have said. Now these things, you should assume that these measurements are persistent and repeatable. Okay, or these devices are persistent and repeatable. What do I mean by that? I mean, let's say you have a color box and then you send in something, right? You have a color box and then something comes in here, something comes in here. This is probably black, this is probably white. And then you put them to another color box here, right? 100% white. Right, because you're sending only the white electron, so again it is coming out white. So what I'm saying is, if you measure an electron as white once, it will always be white. It's a persistent property. Okay, so you should imagine that these boxes have that sort of persistence. You measure an electron as white, it will be white again, it will be white again, and things like that. Similarly, on the hardness side. Okay, so till this point, no confusion, right, on anything. It's pretty simple and trivial. Not trivial, but simple. Now, what is the next sort of question that we can ask on this, right? Now I have given you two properties, black or white, hard and soft, and I've said you can measure this, and the measurement is repeatable or persistent. So, what's a question that you can ask? A question you can ask, and actually which was asked in late 1900s by a lot of physicists, and we'll get into those details, is are hardness and color related, right? This is a question you can ask, right? That is, if something is white, does it improve it? Is it always hard? Does it improve its chances of being hard or soft? So is there some correlation between something being between the color and between the hardness, right? Is it a valid question to ask?
Yes,
it's a valid question to ask. So let's do this experiment. Okay. Let's say I have a color box and I'm sending some input electrons, right? I'm sending some input electrons. Here you've got all the white electrons coming, here you've got all the black electrons coming, whatever black and white may be, right? And then you're sending them to another hardness box. Okay. Again, here there'll be hard electrons coming out and here there'll be soft electrons coming out. So let us say, now look at this experiment setup, the way I've put it up. Now let's say your color and your hardness have some correlation. Okay. Then you would expect that the probability of something coming out hard or soft should be different from 50-50, right? Because if white color electrons are more likely to be either softer or harder, they should be, that should show in the probability, isn't it? And also imagine here, when we do these experiments, imagine that we are sending the electron one by one. Because if you send in electrons all together, there is a theory that maybe the electrons are somehow interacting with each other. We will bust some of those myths as we make these experiments, right? But I need you to understand this as I'm talking. So what do you expect the probability distribution here to be? Do you expect this to be 50-50 or do you expect this to be something different from 50-50?
There is a correlation, then obviously it should not be 50-50.
Correct. So do you expect there is any correlation or not?
can't say.
Yeah.
Definitely there would be some correlation.
Okay.
Why
Good.
should there?
I think it's a 50-50. Where can you go wrong? Yes. Fortunately or unfortunately, it is going to be 50-50. So they are not correlated in any way. There is, and trust me, I think Tammachari said there seems to be some correlation, and I think a lot of great physicists have thought like you, and they have spent decades perfecting their experiments trying to find some correlation. They have not yet been able to find any such thing. Whatever, and it's the same even if you reverse. Same if you reverse, same if you take black and same if you take, you can take any combination of this experiment, doesn't matter. The result is whatever you do, you put it, the probabilities again, the electron will get 50% hard, 50% soft.
In this color and hardness also, what you are saying here is, can be any two
Properties.
measurable
Properties of an electron. Not any, we will go into some particular properties, okay, but that's okay. We will get there, but first I need you to understand how it is, because then when I will tell you those properties, they'll become, okay, they are color and hardness. Think about it like that, right? So that's what it is. So this is an important result in quantum mechanics. These properties are not related. As the smarter among you may already be thinking where this will lead to, think a little bit. There is something that you guys all know, and that is where this thing will lead to. But at this point, let's just leave it here. We will conduct those experiments. So till this point, clear?
Yeah.
Now let's try and do this experiment a little. Let's have fun with this. Let's try and do some other mess and let's see what happens. Okay. I think hopefully, usually playing and messing around is the best way of learning some of these things. Okay. Let's now do this experiment, right? So again, you have some black, some white coming out, and then let's say you put them through a hardness box. Still here it's the same thing, right?
Yeah.
Some here, some here are coming hard, soft. And now you're putting it through a color box again. Now, again, white, black. Now tell me what will be the probability of things that are getting split out. See, here you know it's 50-50, right? Here it is 50-50, okay? But you have taken only the white electrons.
It should be ideally only white.
I don't know ideally what will come out here. You are in, imagine you are in the quantum world. Everything
Yes,
is
we are. I'm guessing it'll be 50-50 in either of those outputs. Again, it'll be 50-50. I'm assuming.
50-50.
Yeah.
Again, even in the following.
Not 50-50.
Yeah, let us say predicted. Okay, let's say black, white, 50-50. There is predict. Anybody disagreeing with this prediction?
First layer 50-50, but second layer won't be 50-50.
So what will be?
It will be 0 actually. I mean, I'm thinking from the polarized and unpolarized concept.
It's
Yeah,
a quantum.
polarized. Yeah, we will get there also. I mean, and even there we'll have fun. Let's see. But remember, in polarization, you're looking at only one property. We'll do the polarization experiment at the end. So two predictions are there, right? Some people think it's going to be 50-50 and some people think it's going to be 0-100. And I also need some reasoning on why people think it is not just a guessing game here. Right? Why do people think it's going to be 50-50? Tell me one. Some people said it needs to be 50-50. Why is it going to be 50-50? You took only the white electrons. The electrons that came out of this as white you took. Okay. Up till here, no question. And this process we said is repeatable. So if you take a white electron and measure it again, it will come white. Any number of times you keep measuring the white electron, it will keep coming white only. Once you have measured it as white, it will remain white. Okay, as you are kind of measuring it again and again. The problem you have done is you have put another thing in between called hard and soft sort of thing. So here we have seen, strangely enough, there is no correlation, so this comes 50-50.
Yeah.
Right? Last experiment was that. We said color and hardness are not correlated. So this comes 50-50. Now we are saying we are taking these 50% of the electrons that have come from there and are passing it through another color measurement. And we're saying what will be the answer. Okay. This is the right answer. The right answer is yes, it's 50-50. Why? It tells you a very interesting thing. It is nothing is, there is no and in these states. It's not like it's going to be white and soft. See, we normally how do we think of observables in the classical world? In the classical world, the way you think about it is, if something has color and if something has hardness, they are two independent things, right? Right. If something's color is there, it's a particular color. How does it matter? The hardness may be whatever, but the color doesn't change. But in the quantum mechanical world, these properties that you talk about are not like classical observables. They are observed, the wave function collapses the point of measurement, that's all. So till that point, it is always in a superposition, it's in no state. You measure it, fine. If you're measuring the same thing again and again, it persists that property. But if you do something else with it and come back, there is no memory. It is not holding it. And the wave function is collapsing at the point of measurement only. This is a very, and we will see it in the polarizer experiment later. See, this one disturbed physicists like anything. This is a very disturbing thing, right? If you really think about it, this is very disturbing. You're basically saying the whole world is just random. There is nothing deterministic about it. You are measuring something as something, and that something can be something else. Who knows? There is absolutely no determinism. You have actually lost determinism here, isn't it? We'll get into more weirder examples of this, but getting what you're saying, right? So there were all sorts of things, right? Some people said, hey, there could be a problem with this measuring apparatus. This measuring apparatus is nonsense. You have not made it well enough. Who knows? Some nonsense is happening. Okay, so people tried making it with all sorts of things, with neutrinos, with silver atoms, even with C60 atoms, buckyballs, right? So people have repeated these experiments hundreds of times with different measuring apparatus, and every single time the answer is the same. The biggest challenge to this came from the great Albert Einstein himself, right? Albert Einstein did not like this. He said, God doesn't play dice. This is nonsense. Okay, and he basically said something called hidden variable theory, right? I think that's a very, very important thing. He said there is some property of an electron that we don't know. If you had known that property, you would know whether it would be white, or it would be hard or soft, white or black beforehand. There is some property, some other property that you don't know of. It's known as the hidden variable. Some hidden variable exists. It all sounds philosophical, right? Nobody knows what the hidden variable is. Nobody has measured the hidden variable. Nobody knows what the hidden variable is. But that's what Einstein said back in the day. And he said, because of that hidden variable, something like this happens. That was conclusively proved wrong by a guy called John Bell. And you should probably, we'll probably not spend too much time because it is going to be very, very complicated. And we don't really need that for our quantum computing per se. Yeah. But if somebody is interested, we can do a separate thing on that. It's not required for this. So John Bell in 1960s was an Irish physicist who conducted one of the most elaborate experiments, I think, known in human history to finally prove that even if you had something like that, it would still not matter. And he finally disproved Einstein, okay, in 1960s. We can get into that. What is another thing they throw at this? Another thing they throw is you're probably sending so many electrons together, who knows? Maybe those electrons are interacting with each other and doing some nonsense like this. So we send it one by one electron, the same thing happens. Some people say maybe there is some substrate here, whatever you are using to either polarize or do something in this equipment, maybe that has some substrate properties where an electron is interacting with a particular part of that substrate that has a particular structure. Due to that structure, something is getting changed and all of that. Right? Again, we have done it with every known substance and the answer remains the same. So this is just for me trying to justify why this result. See, it is not a result we like, but it is a result you have to get used to living with. Because this is the, in fact, I will stop even saying this is the quantum mechanical world. This is the real world. What we end up seeing is an approximation to this world at our scale, that's all. This is the only reality out there. The only reality is electrons and photons, and they exactly behave like this. In fact, it took me a number of years to get there, right? But now I have kind of told myself repeatedly that, boss, this is real. Don't think that is real. That is not real. Okay?
Then if this 50-50 comes from the third box, so with the entanglement, there should be something else.
We'll get there. Yes, it will get very complex. We will talk about entanglement next class. This class, let's limit it to understanding superposition. Okay, but you're right. It will get really, really weird. Okay, and that is why the quantum mechanics math gets weird. Okay, it gets difficult. You get into all sorts of problems, and we will see the solutions to some of that. But first, today's class, I didn't want to get too much into math. I just wanted to make sure I understand this concept. Now let us see. What is the implication of this statement. We have said something like this. What does it mean? Okay, we've said something like this, which said that the measurements are persistent, but persistent under very specific conditions. Otherwise, they are not persistent. Now, one of the biggest results coming out of this is it is impossible. It is impossible to build a reliable color and hardness box, right? And we'll prove it. So you cannot measure both of them simultaneously.
Box which measures together.
Together. So essentially what I'm saying is, let's say you have a box like this, and I call it color and hardness, and I'm sending some input electron here. And let's say it has 4 apertures, right? I can actually do that, right? I can say something like, I don't know, white, soft, white, hard, black, soft, black, hard. BS is bullshit, but yeah. So what I'm saying is, it is not possible to build a measurement box like this. Guys with me on this, on the phone?
Yeah. Sounds like Heisenberg's.
Yeah, coming close to sounds like uncertainty principle, doesn't it?
Yes.
Yeah, so that will be the result. See, that's why I found a novel way to get you to uncertainty principle without actually telling you uncertainty principle, right? You kind of substitute this with the displacement and momentum. What you get is uncertainty principle. So Heisenberg's uncertainty principle in that sense can be derived from first principles. You don't need to have that complex math from Hamiltonian to derive this, though we will use that also, because you need to learn the math, but actually you don't need that. Just from pure experimental first principles, you will automatically get right there. So let us actually try and build that to see the impossibility of that. At least let us all have in our head clearly why it is impossible. Some input. Let's say I put a color box here, right? And then something comes. Let's say this is coming out black. You put an hardness box here, and then something comes as soft. And here you have black soft. Right? Something like that. And from hardness box, this is hard. You're putting one more color box. No, you don't need to put a color box here, sorry. You don't need to put a color box. If it's hard, you know that this is black hard. Correct? And similarly, you do this, you put a hardness box here, you get again the same thing, right? 25%. You get some white, you get, I don't know, whatever. If this is soft, then this is white soft. If this is hard, you get white hard. Just now we showed that once you do this, this is not retained. Right? Once you measure color and you measure hard, it again becomes completely random. It is not like the white property is being retained. Similarly, the black property is not retained. Hence, you cannot build this. The answer will not be this. So if you measure it again, now what happens? Now let us say you send this to a color box again here, right?
It won't be black, it will be white and black.
It will be again 50-50 white and black answer you will get here. So you will not get black here. If you put a color box, simply put a hardness box and measure, it will again 50-50. So you will never be able to do that. So now, what does this tell you? Intuitively, what are you understanding? See, intuitively, if I tell you, what does this tell you, or what is this experiment trying to tell you really, is at the end of the day, it doesn't mean anything to say that an electron is white and hard. It doesn't actually mean anything. It is not that it is not white and hard or it is hard and, no, it doesn't exist. It doesn't mean anything. There is nothing like white and hard. There is nothing like displacement and momentum at the same time. It doesn't exist. That's all. If you take the limit in the classical world, it appears that they exist. That's all. But actually they don't. There is nothing called displacement and momentum. There is either displacement or there is momentum. That's all. Both of them don't exist at the same time at all. It doesn't mean anything. See, one thing you have to understand when you're talking about this, even in your brain, I think for me it helps. Okay, think about electrons or photons and you think about it. Think of them as clouds of energy. Instead of, don't think of it like a wave or a particle. It is neither a wave nor a particle. It is an electron. In some conditions, it seems to exhibit properties of waves. In some conditions, it seems to exhibit the properties of a particle, but it is neither. It is something else. Now, what that something else is, you can, in our dictionary, we can only say an electron. Because we don't have a word for that. We only have waves and particles. Now, what we call it wave-particle duality, that's probably the biggest disservice. It kind of makes us think that it is as if a wave and particle. No, it is neither a wave nor a both. It is not both. It is something else. What is that something else? We don't know, because in our natural language, we don't have anything. So we just say, okay, something. And we call it an electron. Okay?
Intuitively, it feels that we should just use the capability of electron to behave in either way, based on the condition, and then just try to solve.
Do something with it. But when you think about it like some energy cloud traveling. Now that energy cloud, in some parts, that entire energy cloud in itself behaves like a particle. Okay, because at that part it is like a particle. That energy cloud can also behave like a wave under certain conditions, especially when you're doing diffraction and things like that. Okay. And out of this comes the uncertainty principle. So now you know why it is uncertainty principle. It is uncertainty principle because it is not about measurement. See, that is the biggest problem people have. It is like, oh, if I have a better measurement technique, I can measure it. No, it is not about how well you can measure. You can create the world's best measurement, you still can't. Randomness is intrinsic. See, in the classical world, we are taught that randomness is a question of measurement. So for example, if I toss a coin and if I tell you whether it's going to be head or tails, okay, we say it's a probability is 0.5 or something because we don't know, because it is random, it is probabilistic. It is not random. If you can actually measure the forces acting on the coin at every instant of time, you can exactly predict what side the coin will fall. If the initial conditions are given for you and if you can calculate every force acting on it, you can clearly say whether the coin will fall head or tail, right? So the coin is actually deterministic. It is our ability of lack of measurement that makes it probabilistic. So the randomness is not intrinsic in the classical world, and it's a very, very important thing to realize when you get into, in quantum world, randomness is intrinsic. Things are random intrinsically, not because of measurement. An electron is always going to be random. It's not a question of measurement. However much you try and measure the electron, you can't measure it. Okay. I hope that makes it clear. This is the one thing that you should be very, very clear in your head as you're trying to build algorithms later on, right? Because at the end of the day, the problem you face is this. Imagine in this intrinsically random world, you will have to create algorithms that give you deterministic answers. Correct? That's the problem, right? 2 plus 2, even in your quantum computing, still has to be 4. You cannot have something else. But how do you make it when the underlying substructure is completely random? The underlying substructure is not deterministic at all. You can't even measure it. Okay. So that's going to be the challenge. And that's why we have to spend some time understanding this and the math behind it so that you can start designing those algorithms like that. And the strangest thing is, even in the classical world, it's the same thing. We just don't seem to notice it. You are noticing it now because when the IC chips are getting smaller and smaller, you are practically approaching quantum sizes. Right? But typically you don't, right? We don't see those effects. You don't. And again, quantum effects are not only for small things. Quantum effects can be observed at the highest levels also. Like you and I also exhibit quantum mechanical effects. Just that our measurement tools are not precise enough. That's the other thing. It's not like, don't think only electrons are behave in a quantum mechanical way and the rest of the world doesn't behave. Everything in the world behaves in a quantum mechanical way. That is the only way to behave. There is no other way to behave. Only thing is we cannot measure it. People who can measure it can intrinsically see randomness. Okay. So that's all. So don't be in that thing saying that okay, this is only electrons, I don't care. We have observed quantum mechanical effects in black holes also at the other end of the spectrum, right? So quantum mechanical effects occur everywhere. In fact, they're the only true effects to occur. So how come they won't occur? Everything is finally electrons and quarks and whatever. So it's not like you're not going to do that. Now we will up the game a little bit. We will have a little bit of fun now. Okay. So I'm going to create an apparatus here, which we will use some further experiments to gain some further insight into what is going on with electrons. Let us say you have some hardness box. Today you should dream about hardness and color boxes by the time I'm done with this. Let us say you put two mirrors here. These mirrors do nothing but just reflect the electron beams, right? This is actually called the Zach-Mender experiment, but we'll do it in a more informal way to understand it before we get into the formal experiment. And let us say here you put some sort of beam combiner. All that it does is combines both of these beams and sends an output. So let us say this is our new apparatus. We have usually we used to have just this, right? We used to have a hardness measurement or a color measure box. Now I'm saying put two mirrors to reflect the beams, combine them and move them. Okay, that's all that I'm saying. And these beams do nothing but combine. They are not actually measuring anything. Okay, they are not measuring anything. Measurement only happens here. The hyper-intelligent monkey is measuring only here. At this point, we still have hyper-intelligent monkeys only. So it's measuring here. This is just two mirrors. And then think of this as some sort of beam combiner. Okay, that's all. It's combining two beams. Now let's do a few experiments on this. Now, experiment 1. I am putting another hardness box here. Okay. What is the probability? Whatever, soft and hard. Predicted. What do you think will be the probability of electrons? You are doing one measurement here, you are doing another measurement here. What do you think will come out? This is easy, man. Come on, guys, you have to guess. Somebody on the phone. I want somebody on the phone to say something.
50-50 again.
50-50.
50%. Anybody has a different answer? This is the right answer. Right, now if you want to explain this, see, once you put an electron could have either gone through the soft path or the hard path. There are only two paths for the electron to take. You are combining them so that kind of becomes equal. Actually, what is the whole point of this apparatus? You could have taken this as this. It will be the same thing actually. Right? Because anyway, they're all getting combined. So whatever was given soft will come out soft. Whatever was given as hard will come out hard. Because I said the measurement is persistent.
If we are throwing one electron per, then
No, it is persistent if you are not measuring something else. See, if in between, if I had measured color and again I had measured hardness, then that is gone. Is that okay? You guys getting what I'm saying?
Yes.
Then what is the use of combiner here, Srini?
There is in this particular experiment only to confuse you.
Okay.
In this particular experiment, just to confuse you. But we will see a use for that in some.
seriously started thinking Mirror will really reflect it right if it's very
yeah. Don't get into all of that. Yes, see, right now we are expecting perfect mirrors. But ideally, in reality, you cannot even shoot a beam of electrons completely straight. It is not possible. There will always be dispersion. Okay, you cannot even shoot that. So these straight lines are all in theory. In practice, there will be some interference, and there will be some. All of that will happen, but we don't have to worry about that, right? Because if you that we will worry when we're doing the math. In the math, we will worry. This is the conceptual understanding. So this is right.
The same set of electrons may not be coming out as soft.
Exactly.
Different set of.
Now let us say experiment number 2 here. 1 and 2 are relatively easy. The fun starts at 3, but we will do. Okay. Now what happens? 50-50, right? Yes, you are again right. But this is just for warming up. We will get to the place where you guys will have fun. Okay. Again, no confusion here, right?
Yeah.
Is there any confusion here?
No, Srini.
No. Okay.
No confusion in Japan.
Now we will get to the third experiment. A little variation on this. We get to the third experiment. Now what is this? Sorry, forgot. Here, let us say we have one hardness. Okay. The same experiment like last time, nothing much. The only difference is here I am sending, let us say, only white electrons. I am sending only white electrons into this box. I am sending only white electrons because how am I getting white electrons? Imagine there is a measurement before that where I have measured, and whatever comes out of the white aperture, I am sending it into our great aperture with 2 mirrors.
50-50.
Right? And we have now, let us say, whatever, black and white and prediction. One prediction I got is 50-50. Anybody else thinks? Any other answer, or this is the answer?
This white electrons already, once we have the H observer there, it's gone, it's no more white. So it doesn't matter. Yep.
Now you should be saying, what the hell, man? You're just making a fool of me for the last 45 minutes. Think, this is where the fun begins in quantum mechanics. Okay, it's not as easy as I told you. People from Schrodinger to Planck till Einstein, they suffered for decades trying to understand what this nonsense that goes on.
But actually,
has this shocked you first, guys? I want you to be shocked. You need to be first shocked. Yes, we will get to learning, hopefully. Next class, we will learn. Don't worry about this. There are rational, logical explanations for whatever is going on. But first, so now what has happened? You have an electron beam of white electrons or whatever we measured as white sent through. Something came out. 50% you should say came here, 50% came through here, and all of this they got split up, and according to whatever we have known, once this is done, they all become white or they lose, it doesn't matter. So out here when you will measure again, they should be 50-50. That's what we have been told till now, right? And we all were happy in our understanding. But it did not. It behaved in a weird way. Like somebody was saying, what the hell is going on here? Apparently, that's what Schrodinger said when he finally saw these results. It's like, it doesn't make sense. So everybody agrees with me here?
but then this actually means that we are able to say and get it to non-dual state and predictably.
No, it does not, and we will see why. Anybody else?
It's not consistent with the earlier experiment.
Yes, it is not.
Okay. What?
What changed? When I sent only electrons, the only thing different from that and this, I sent electrons having a particular property in. How is that different within the apparatus to the other one? Anyway, we will get there. We will see. Because see, this is what happens. Now, the experiment results cannot be, all the experiments that I've told you right till now are the experiments. Okay, so there is no point wasting your time in thinking the experiment result is wrong. No, the experiment result is absolutely right. People have tried finding fault in this for decades. Nobody has been able to find a fault. All these experiments are valid. Okay. What we have to do is find some sort of rational explanation to this behavior. Okay, because this is how these electrons or photons actually behave. When you talk spin or momentum or whatever you are measuring, this is how they will actually behave. Right. Now let's think about it. See, let's put something called a barrier here. Okay. We'll talk about it. Now let's just say there is something called a barrier. Now this barrier is something that you put in, it will actually stop the electrons on that particular flow. So wherever I put a barrier, that will stop. So for example, if I put it here, all the electrons here will be absorbed, so nothing will flow. Let's think about a situation like that. And that is experiment 4. Let's just say 4. And let's just try and understand what happens. We will get to an understanding of the other one. So if I put something like a barrier, it basically says that you will stop the electrons. Right? The electrons you can stop. So only one set of electrons are flowing. Okay, one set of electrons are flowing, and this is what is happening. So if you do this sort of a thing, what is the result that comes out?
50-50.
Yes, the result becomes 50-50.
It's similar to the first or second experiment, right?
Correct.
Yeah.
So if you do this becomes 50% and this becomes 50%. Just makes it even worse. Even worse. Actually, if you people remembered the double slit experiment that I talked about in the first lecture, it has something akin to this.
Yes.
You are putting it on one detector and you are measuring it, the inference, it kind of gives you an interference pattern. Otherwise, it just gives you basically two patterns, like 1 and 1. Right? So it gives that. So, sorry.
That superposition was not happening if I close one slit.
Yes. But the bigger problem is now, see, something really weird is happening. Something really weird is happening once we're seeing this. When I removed that barrier, everything was coming white. When I put in the barrier, it is going back to its expected behavior, which is 50-50, which is what you would normally expect it to behave it as. Now, what is going on here? See, forget about what is coming out. For a second, let's try and understand the flow of electrons and things like that. If you put a barrier here, what would you expect? You would first expect that the output is down by 50%. Okay, that's the first thing you should expect, right? And this happens. The output is down by 50%. So you know for sure that something is getting blocked. There is no question. Okay, nothing is passing out on this wave. So only half of it is actually coming, whatever the volume that you use. Now, let us think about what path the electron could it have taken. In experiment 3, first let's go to experiment 3 for a second and understand one more thing we needed to understand before I came here. In experiment 3, if I put this, it came 100% white. So now we know that if you do this measurement, then you should get 50-50 only, because we proved in previous experiments that that is what happens. Correct? Now, if you look at experiment 3 and ask the question, which path, the electron that I'm measuring here, which path did it take? Okay. It cannot take the hard path. Why? It cannot take the hard path, because if it had taken the hard path, then according to 4, it should have given 50-50. No. You understand what I'm trying to tell you here? So it cannot take the hard path. It could not have taken that path in this result. Can it? Or maybe in experiment 4 is what we'll talk. Sorry. No, 3 only. Yeah. Can it take the hard path? No. Can it take the soft path? The answer is again no, because I would have put the barrier here, then it would have come 50% again. So it cannot take the, see, it could not have taken the soft path. Could it have taken
Both the paths?
Taken both paths?
Maybe.
Could it have taken both paths at the same time?
Yes, with different probability.
No, probability is a probability, but but could it have taken simultaneously both paths?
Yes, maybe true. That's why it's happening.
No, it cannot. It cannot take both paths simultaneously because you can block. What is the only other alternative left? Can it take neither path? That is also that's also nonsense, because actually seeing some output there. So look at the problem here. The problem is the electron could not have taken any path, could not have taken the hard path, could not have taken the soft path, could not have taken both paths, and could not have taken no path. So what path did the electron actually take? The electron took none of these paths. The electron was in a superposition across this entire apparatus. So what does that mean? Are you getting what I'm trying to say here? The electron was simultaneously here, everywhere with a certain wave function, with a certain probability. The electron was nowhere. The electron was everywhere at the same time. That is the only explanation you can give. So the way to understand superposition is this. The way to understand superposition is, see, unfortunately, a lot of times when last time I told you, I had the worry that people understood superposition as some probability function. Yes, we mathematically solve it like a probability function because the electron being somewhere is always 1. But the electron being at any given point in place is 0. You understand what I'm saying, right? If I say, will the electron be here? It is 0. It is here, it is 0. It is here, it is 0. It is 0 everywhere, but it is somewhere.
Then how does it explain the 100%?
It doesn't explain. It just says that the electron chose to behave like that in that particular setup, and it's completely random. That wave function collapses like that. That's all that you can say. You cannot say this is why it is 100% or. See, the biggest myth is all this while when I was doing the other experiments, all of you were thinking it is some deterministic behavior I am understanding. That is the myth I wanted to bring. You have not understood anything. It is not possible to understand anything. Are you getting what I'm trying to say? I created an illusion of knowledge. And this is what actually happened in quantum mechanics also. When people were doing a lot of experiments, it was giving results. So you start believing that you know what is happening and those results are somehow deterministic. Those results are not deterministic. Those results are not at all deterministic. The wave function can collapse. It can collapse wherever you want it to collapse. For example, if you have an x, you have 0, the wave function can collapse here. The wave function can collapse here. There is nothing like the wave function has to collapse here. No, the wave function can collapse wherever it wants. The only way you can control this is if you control the probabilities, which is basically, see here, you have given 1 to 1. So you can control the output to some level. What I'm trying to say, last time in superposition, we said, right, if you have 1 by root 2, 0 plus 1 by root 2, 1. If you control these, then you can say over a period of time, half the time it will be 0, half the time it will be 1. But if you don't control this, in a natural scenario, you are not controlling this. If you are not controlling this, it can be anything. You cannot control this. Hopefully, some idea you have got on superposition. Maybe we will do one. If you've got 5-10 minutes, I can do the polarizer experiment and go through it. Do you have 5-10 minutes? I know it's 12:01.
Yes, I have a question though.
Please, there will be many questions.
Now,
Ask, think about it also.
Why is it that the probability of that electron existing is only within the apparatus? Why can I say it's somewhere else also?
Yeah, you can, but here we are calling it a system just to make our life easy. It can ideally be anywhere in the universe.
Oh.
The wave function is not, you are trying to limit it by something. Otherwise, you will probably say at the boundary, I am putting something that will absorb all electrons. Something, put something.
Right. So we're putting that ourselves, but there's nothing stopping me from saying that it can exist anywhere.
It can exist, anything can exist anywhere. It is just a wave function, that's it. It is not bound. See, in fact, the bigger question that nobody asked me, see, here I put a barrier. It adjusted somehow. It's at 50-50. Now, how does an electron going here know that there is a barrier, there that the electron can't go? It doesn't, right?
It went there and got back.
It self-adjusted. So how is that happening? How does this electron know? These can be millions of miles away for all I know. this path and this path you can put it wherever. You can put it on Earth and the Moon, and still it will adjust. How is it even knowing that something like this is going on? Same thing, right? In your double slit experiment, as you're putting a detector, the probability is changing. How does it know if you're detecting it or not? And again, the word to know, you have to be very, very careful to use the word know in quantum mechanics. You don't know anything. You don't know anything. It's only an experimental setting where you're measuring something. It's only measurement. Be very, very careful, okay? Slap yourself every time you start saying, I know something. You don't. You cannot know anything. There's nothing to know. Okay? You measure. You just measure. There is, if you put a detector and if you are measuring, somehow it is following the exact way how particles would behave. You put the, and the funniest thing is, you put the detector there, you switched it off, it is gone back to its previous behavior. You switch it on, it is as if it is watching if you are watching or not, and then self-adjusting. Okay? But it is not about that, right? It's about understanding if you are measuring, the wave function collapses, and the wave function can collapse in any way that it wants to collapse. That is the non-determinism part of the, and that is why controlling the probabilities, or what we call the actual wave function. This wave function controlling is very, very important. Only then you can build some quantum circuit that actually gives you a meaningful output. Otherwise, you cannot control the output. See, again, I talked a little bit about, see, the funniest problem is this, right? Now, this whole thing, if you really historically try to understand this a little bit, now let's just say common sense here. Let's say there is a piece of metal here. Okay, let's just say there is a source of light, and you're kind of hitting a metal, and some electrons are bouncing out. Let's say there's a sun or something, right? This is some metal plate, right? You're kind of doing it. When you do this, so what does common sense tell you? Common sense tells you, if you increase the intensity of the light here, if you put brighter light here, okay, more electrons should come out, and electrons with higher energy should come out. Correct? You should say higher the intensity. I'm telling all this because this is where this whole thing came out. Higher the intensity, higher the electron energy. Makes sense? If you increase the intensity, the electron should fly out faster with higher energy. But when you actually plot it, so if you for example, rig a circuit first. If you rig a simple circuit with some voltage here, some voltage here, and then let's just say on two sides you have some potential, and then light is suppose you're shining some light, okay, you're shining some light on this, and then some electron has to kind of fly out and move here. Okay, you put some argon gas or something, and if you put it enough, you'll see a spark, right?
Yeah.
See, that's what happens. Everybody clear on the phone what I'm trying to say here? You put a simple potential here.
Yes.
Okay, you do that. Now, what is the problem? Now, ideally, if you put some potential here, at some point, this electron jumping from here to here has to overcome this potential. Correct?
Yeah.
So, if it jumps, then you can measure a current. You can put some ammeter here and measure the current flowing through this circuit, right? Now you can increase the light intensity here. Okay, keeping this voltage constant, and see what happens. And then you draw a graph. Till some point there will be some Q critical, right? Q0 or something, till which point no electron will flow. And then as you kind of move it, it will be, this is what should happen. Correct? You maintain this, and by doing that, you can check for what intensity, how much current is flowing, and things like that. You can keep controlling the voltage, you can keep controlling the intensity here and see what happens. Now, the problem that you see is, for a given voltage that you put here, increasing the intensity does not seem to have an effect. You understand the problem I'm talking about? You increase the intensity of light here. You put brighter and brighter and brighter light. More electrons don't seem to be jumping. The electric current seems to be kind of right there. But you change the light of color, more or less electrons seems to be jumping. You understand what I'm saying? Keep the intensity constant. Change the color, change the frequency of light. You change the frequency of light, you will see more electrons or less electrons jumping. See, this was the problem. This was the problem with black body radiation. People, you would have studied black body radiation. Max Planck black body radiation. The black body radiation, the current flow or the energy is somehow doesn't seem to be dependent on the intensity, which is the square of amplitude, but rather on the frequency, which is very, very strange, which is not what it is supposed to be. Same reason you will see, right? If you are cycling, I think you guys are too young to see cycle dynamo lights. You guys seen that? Usually cycles used to have lights which are a dynamo. You pedal and the light light goes. Right? What happens? The intensity doesn't change. When you are pedaling it slowly, it is small yellow color. When you pedal it strong, it becomes white, orangish white color. The frequency changes. Have you ever seen that in dynamos when you cycle? Why does that happen?
Yes, I have fitted it in my cycle. Ah,
good. So go home and check it. The color changes, the frequency changes, not the intensity. It is a very, it's a simple problem, but a very difficult problem to explain on why that happens. And by the way, that is why Einstein got the Nobel Prize in 1905. He didn't get it for relativity. He got it for explaining the photoelectric effect, which is essentially this. He said light is quantized in terms of energy equals h mu, where h is the Planck's constant, mu is the frequency, also written as hc by lambda. Lambda is the wavelength, c is the speed of light, right? So this is the equation, right? This is the famous equation of Einstein, which explained this. So light intensity or the energy in light is not dependent on the intensity, but rather on the frequency of light that is flown. And this is what comes in. And this is what essentially explains also, like if you're trying to understand quantum mechanics, this is kind of the starting point of all of that, right? And then you have de Broglie's equations and things like that, which you should probably study. But I wanted to make sure that this is the key. This is the historical justification for coming here. And once you start doing this, once you start doing energy is quantized or light only comes in this, we will see the polarization experiment and see the problems that Einstein got himself into by trying to explain that light is quantized and light's energy is actually to the frequency. He got himself into a problem, right? What was the problem? Polarizer experiment everybody has done in high school, right? What is the big deal? Everybody has done it in high school. So if you have a polarizer which is polarized in this direction, you send light, only light in this direction will go through and light polarized in the opposite direction will not go through, or in orthogonally, white will not go through, right?
Yes.
It's a very, very simple polarizer. Everybody wears Polaroid glasses also now. So that is what it is. Now, where did Einstein create a problem for himself is now, it's so simple actually, but now let us say I send in light at some angle theta, correct? Or some angle alpha, let's say. Now what happens? You can write E alpha as what? Some E0 cosine alpha plus E0 sin alpha. Correct?
decomposition.
Or yeah. Now this part can go through and this part can't, right? Correct? Because it's polarized in this direction. So the vertical direction will not go through, only the horizontal will go through this polarizer if I put it at some angle, right? So what happens now? What is the energy after polarization? It has become E0 cos alpha. Because the sign component of the energy got lost because it did not actually go through. Correct. Of course, if you look at the magnitude of this, then it is E0 square cos square. So it's basically E0. So here you have E0 cos alpha, right? So how much percentage went in? Cos alpha percentage went in. If when cos is equal to 0, everything will go in. Yes. Cos 0 is 1. If cos is 90, nothing will go. Now see this simple thing. There is nothing. There is no problem here. But now think about it. If you send one photon at this angle, okay, if you are sending one photon at this angle, what happens? You are saying photon is a bundle of energy that is indivisible. So it is h nu. And the light frequency that you see, it hasn't changed in the other end also. The frequency remains the same. Or the energy remains the same. So, but only cos alpha. So you cannot split a photon. You cannot split a photon. But there is only some energy going in. Your classical mechanics tells you that only this component can go in. See, Newton knew this. Einstein. It was a nightmare for Einstein. Because Einstein got this Nobel Prize in 1905, but he was not at all happy. He was writing papers from 1902 saying, I don't believe in this thing. Because for him, so what is the only way to explain this? The only way to explain this is no one photon can be split. It is not possible. But if you send in a beam of light which has, I don't know, 10 to the power 18 billion photons or something, then some photons will go through and some will not go through, to make sure that the energy remains constant at the other end. But all these photons are completely same. They are all identical photons. The experiment, the polarizer remains the same. But which one goes through and which one doesn't go through seems to be a completely random phenomenon. You understand the problem with this? Because in classical mechanics, the same object in the same experiment has to be acted on exactly same. You cannot have difference. You cannot have randomly different things being acted on differently. But here that's exactly what is happening, right? Understand what I'm saying? The same experiment again, like that. Same experiment, because the wave function collapses in some weird way. You don't know in what weird way it collapses. So you can, you can compare it the same experiment like this. You can compare superposition of these two states. Some superposition of these two states that the electron lives in. It doesn't live in this polarization, it does not live in this polarization. At the point of measurement, it may choose to live in this direction or it may choose to live in that direction. If it chooses to live in this direction, it won't go through. If it chooses to live in this direction, it will go through. But look at it. They are all individual electrons, photons. You can shoot them one after another also. They will adjust so that the final energy becomes like this. How the hell do they, how does one electron know what the next electron will do? It doesn't know. But it works out like that. Which is absolutely mind-bogglingly crazy. It doesn't make any sense. It doesn't make, and in our classical world, it makes no sense. Then how can electrons or photons, one after another, even if you shoot one after another, one will get through, one won't get through, something will get through, something. Which one, beforehand, you cannot say this will get through or not. There is no way in hell you can say that this particular electron will get through or not. Because the moment you measure it, it can choose to be whatever. Completely randomly.
Because it is adjusting to the past.
But how does it know? That nobody knows. That is why Einstein was so crazy. He said action at a distance. He said it's all nonsense. That hidden variable theory was exactly that. There is some variable that is determining the polarization before you measure. You just don't know. was the big argument put together by Einstein for close to 20 years still on his deathbed. The tragedy was he was such a genius in all other sides. Here he was completely wrong. In the sense, there is no hidden variable here. There is nothing. An electron will behave exactly, or a photon will behave in this manner only. Okay. You get this experiment. This is a key experiment. It's a simple experiment. It's not a great experiment. But the thing to understand is, so we can never say if it gets through or not. We can obviously say it with some probability, but those probabilities are also empirical. How do you measure those probabilities? Measuring it a number of times. You cannot, of course, in quantum computing, we will try and define those probabilities for us to build those gates and things like that. And there are ways you can do that. But in nature, normally, those probabilities are empirical. Okay, guys, hopefully you got some insight into superposition today. We will do entanglement next time and it's going to be a lot worse.